Well, in this video, I'll be taking a look at the Achieve Section 2.4 homework assignment with you. There's not a lot of work to show in many of the problems. It's just using the concepts of continuity and then left-hand continuous and right-hand continuous like we talked about in the notes. So in several of the problems, you won't see much that I had to do to work it out, but I'll try to explain the logic that I used in order to answer the corresponding problems. So now when we look at this together, let me go ahead and pull up the Achieve homework page. This is section 2.4. You can see that this first problem asks us to consider the graph of a piecewise function, and it graphs out this function in red. It's asking us to state whether the function shown in the figure is left continuous only, right continuous only, or discontinuous at x is equal to 1. Okay, so if I look at x equals 1 here, you can see that in this picture, f of 1 has a solid dot up here, which is the same y value as what the limit as x approaches 1 from the left is approaching. So I can say, well, that by definition is a left continuous function. So you'll see here in my work, all I had to do is say it's left continuous since the limit as x approaches 1 from the left of f of x is equal to f of 1. Okay, for the next problem here, we have a slightly different function given. Mine is asking, it says the function has a jump discontinuity at x is equal to 3, and then just true or false. Okay, a jump discontinuity would be like what happens at 5, where there is a finite number of y values difference from the left-hand limit to the right-hand limit. That is certainly not what happens at 3. Anytime you just have a hole in the graph of the function and the limit from the left is equal to the limit from the right, that's called a removable discontinuity. We could remove that discontinuity by reassigning f of 3 as being the y value that fills that hole in the graph. So there is a discontinuity there since there is a hole, but that discontinuity is a removable discontinuity. So this answer is false. For our next problem here, again, a graph. And in this graph, it's asking me to find the point C at which the function has a removable discontinuity. So in this one, that's pretty much the same as the last one. You can say, well, removable discontinuity is when the left and right-hand limit go to the same value, but the function is not defined at that value. That only happens at x equals 3 here. So I can say, well, the value of x is C is 3. Now, in order to remove that, what value should we make f of c equal to? And if you track this open circle back over to the y-axis, it looks like it's right in between 4 and 5. And sure enough, it was. It's 4.5. All right. For the next one here, let me bring back up this. When we're looking at this one here, we have our linear function, just 5x plus 7. Well, it's not a linear function. It's the combination of a linear function and a trigonometric function. But I know in the laws of continuity, it says that any combination of continuous functions is continuous. So since 5x is a continuous linear function, sine x is a continuous trigonometric function, the addition of the two functions is still a continuous function. So I can say f of x is continuous. Again, no real work to show other than the logic there. For the next one here, let me make sure that that doesn't disappear. Maybe. Here we go. So now for number 5, it says determine whether 4 over 5x squared plus 7x is continuous. Okay, the numerator is a constant function. That's continuous. The denominator is a quadratic function. That's continuous. But the problem here is that in a rational function, you might say, yeah, but wherever the denominator is equal to 0, it's not going to be continuous. Well, 5x squared plus 7 is a parabola that shifted upward 7 units. It's never going to touch the x-axis. So I can say since the denominator is never 0, we know that this overall rational function is always continuous, and thus I chose that. For number 6 here, it's asking me to determine the point at which 1 over x minus 1 is discontinuous. And so you'd say, well, it's discontinuous whenever there's a gap or a hole. I know there's a gaping gap at the vertical asymptote x equals 1, because we know a rational function has a vertical asymptote whenever the denominator is 0. So you'll see, well, I set the denominator equal to 0. I knew x equals 1 was going to be my vertical asymptote. I even went ahead and graphed out what 1 over x minus 1 would look like over here to show it definitely has a discontinuity at 1. And that type of discontinuity is called an infinite discontinuity. So you can't remove it. It's not a finite number of y value jump from here to here. It's an infinite jump. So we can say, okay, it's an infinite discontinuity. And since f of 1 is undefined, you know it can't be left continuous or right continuous. The whole definition of left continuous is the limit as it approaches it from the left is equal to the function's value at that point. The definition of right-hand continuous is that the limit coming in from the right is equal to the function's value at that point. F of 1 is undefined, so it can't have left or right-hand continuity. And so we just say it's neither left nor right-hand continuous. Now the next one here, I liked this one. It gave me a rational function, except the denominator was an absolute value. So x minus 8 over the absolute value of x minus 7. And again, I wanted to go ahead and think about what the graph of that is going to look like. I knew that the graph would have a vertical asymptote whenever the denominator is 0, and that's going to be at 7. So all I had to do is set the denominator equal to 0 and get the answer to that first question. Now, I have that vertical asymptote at 7. Well, anytime you're to the right of that asymptote, the x minus 7 is just going to be the absolute value of the denominator is just going to be x minus 7. So your asymptote is going to be x over x, and I'm talking about the horizontal asymptote. The fraction of the leading coefficients would be a positive 1. However, when you're for values of x less than 7, that absolute value of x minus 7 is really a negative on the group x minus 7. So your horizontal asymptote off to the left is going to be the leading coefficients 1 over a negative 1. And you'll see that's why I have the horizontal asymptote y equals negative 1 to the left. Now, is that really relevant to solving this problem? No, but I thought it was cool. So I get my function drawn in. I can say, well, anytime you're going to have a vertical asymptote, you're going to have an infinite discontinuity, because in this case, both the left and right-hand limit are going to negative infinity, but that is not a limit that exists. So you'd say we have an infinite discontinuity. And again, that's because f of 7 does not equal the limit from the left or the limit from the right. And so we can say there is an infinite discontinuity, and it's neither left nor right-hand continuous. For the next one, it's just asking if this function has a discontinuity at t equals 2. And I can say, well, of course not. I put false. Why did I put false? Well, can you plug a 2 into that denominator and get a 0? No, it'd be 2 squared minus 2. It'd be 1 over 2. This function is not discontinuous at 2. It would be discontinuous. You could factor that denominator and say, well, that denominator would factor to be t and t minus 1. So it would be discontinuous at 0 and at 1, because that function is not going to exist at 0 or 1. But 2, no problem. Number 9 here. Again, a rational function. I have x plus 1 over 4x minus 7. First thing I did is I went ahead and said, well, let's find the vertical asymptote. Vertical asymptote is going to be when 4x minus 7 is 0. That ended up giving me x equals 7/4. So I went ahead and drew in my vertical asymptote, and then I drew in my horizontal asymptote. My horizontal asymptote is going to be at the fraction of the leading coefficients. Since the degree of the numerator and denominator is the same, I just take the fraction of the leading coefficients, 1/4. So I said, well, y equals 1/4 would be my horizontal asymptote. If I plug in an x value greater than 7 over 4, it's guaranteed to give you a y value greater than 1/4. This region's going to approach the horizontal and vertical asymptotes like this. since my denominator was degree 1, it had to have the opposite behavior as it approached that asymptote. So this side goes up, this side's going to go down and approach the horizontal asymptote from below. Didn't even have to plot any points out to know that that's what the graph of that rational function looks like. Now I can easily answer the questions. I can say, well, clearly there's a discontinuity at 7/4. Yet again, it's an infinite discontinuity. It will always be an infinite discontinuity anytime there's a vertical asymptote. And then, is it continuous from the left or right? Nope. So again, neither left continuous or right continuous. A lot of these questions are pretty redundant as far as the answers. And so is this one. Notice what I did here, guys. They gave me a negative fractional exponent. I had to understand that that was a fraction. So I rewrote f of x. My f of x was 9 times x plus 3 to the negative 2/3 minus 4x squared. Okay, so the minus 4x squared is a continuous function. I'm really not worried about it. It's this first part that's going to cause the discontinuity, because 9 times the group x plus 3 to the negative 2/3 means 9 over x plus 3 to the positive 2/3, and then I'll put my minus 4x squared. Okay, now what's going to cause a discontinuity in this? Well, it's going to be when this fraction does not exist. So I said it's going to be discontinuous when the denominator of that fraction is equal to 0. That's going to happen at x equals -3. So now I can say, well, yeah, it's going to have a discontinuity at -3. It's going to have a vertical asymptote there. And so I can say it is discontinuous at -3. It's going to have an infinite discontinuity because, again, it's a vertical asymptote. And whenever that's the case, it's neither left nor right continuous. For number 11 here, we're given a piecewise function. Give peace a chance. Notice what I did for my piecewise function here. So f of x is equal to the cosine of the angle 1 over x minus 3, or it's equal to 0. Now, the first one is valid for all values where x is not 3. And then, of course, if x is equal to 3, your angle doesn't exist. So it says when x is equal to 3, let's just let my f of x be 0. Okay, now, what when I thought about this, and I'm going to say, well, the original function would be discontinuous at 3. The f of x is still discontinuous at 3. Why is it discontinuous at 3? And the reason it's discontinuous at 3 is because the limit as x approaches 3 of this function doesn't equal 0. So it's not like plugging in that 0 when x is 3 filled in a hole in this function. This function does not have a hole in it. Let me go ahead and show you my work I did for that. Here's your cosine of 1 over x minus 3 here. So in order to see the limiting value, I'll go to my table of values. Notice I tried to approach 3 from the left-hand side, and I said, well, if the limit as x approaches 3 is 0, then this function is going to be continuous at 3, because when x is equal to 3, my y value is told to be a 0. That doesn't help. Look what happens as x gets closer and closer to 3 at 2.999, it's 0.56238. When I go to negative or 2.49s, it's negative 0.9522. When I go to, well, that's the same thing, 2.49s accidentally. When I go to 2.59s, it goes to negative 0.99936. Now, I almost thought that the limiting value should be -1 here after that step, but it's not. Notice if I go to a whole bunch of 9s, it goes away from -1 and it starts to get less negative, negative 0.90727. So what this is telling me is that this function is just going erratically. It's not approaching any one number, so there's no limiting value as x approaches 3. Now, of course, I just did the left-hand limit. You could have also done the right-hand limit here. You could have said, what about 3.001? At 3.001, not surprisingly, my y value is the same as it is up here. What if I do a bunch of zeros and a 1? Is this going to approach a y value of 0? I guarantee you it won't. That 0 in this problem does not help. So you said, well, okay, how am I supposed to answer this? Well, all this is a case of is that as x approaches 3, the y value does not approach any one number. There's just no limiting value. So it's not a jump discontinuity because it's not like the limit from the left and the limit from the right are some finite difference away from one another. It's certainly not an infinite discontinuity. These numbers are not going to infinity or negative infinity. This is a different type of more complicated discontinuity, which your problem or which Achieve just calls it a severe discontinuity. So it's not one of our typical cases where we have a jump discontinuity, an infinite discontinuity, or a removable discontinuity. This is just what's called a severe discontinuity because the limit from the left and the limit from the right don't even exist. So we know that no matter what value of y we let x equal 3 have the y value of, it's irrelevant. The limit doesn't exist that. So we call this a severe discontinuity, and you'll see that that's the way I answered it here. I don't think there's any problems in the book that model that type of question. Now, unfortunately, number 12, exact same type of question here on Achieve. And you can tell it's the same type of question because your function this time is a sine. What do you know about both the sine and the cosine? Well, they're cyclical functions that keep on going like that forever and ever and ever. So if I ask you what happens to the sine of 1 over x plus 9 as x approaches negative 9, again, if you tried to find the limit from the left or the limit from the right, it's not going to exist. So we know that this function is discontinuous at 9, but no amount of y values is going to plug in that discontinuity because it's not a removable discontinuity. So the fact that we tried to make f of x a piecewise function doesn't help. And so you're still going to have a discontinuity at x equals negative 9, and it's that severe type of discontinuity that cannot be handled. So it's not a jump or a removable or an infinite discontinuity. It's what we call a severe discontinuity. Okay, guys, for number 13 here. Again, we have a piecewise function, but this time at least both of our functions are just algebraic. We have a quadratic function, f of x is equal to 6x squared anytime x is less than or equal to 2. And f of x is the linear function 22 minus x for x greater than 2. All right, so it's asking me to compute the left and right hand limits. All right, well, the left hand limit. For any value of x less than 2, I know that this equation is valid. So the left-hand limit as x approaches 2, you just plug a 2 into this function. You get 6 times 2 squared, that's 6 times 4 is 24. Now, the right-hand limit, for any value of x greater than 2, we can plug it in this function, and when we do, we'll get 22 minus 2 is 20. Now, what we know in this case is that, and let me make sure I drag this down to see if I'm answering the question. Yes, the left-hand limit is 24, the right-hand limit is 20. And now it's saying, is this left or right continuous? You can tell that without even doing this, because up in your equation, you can see, well, the left-hand limit would be what happens when I plug 2 into the top equation. And f of 2, since x is defined to be 2 in this equation, that's also in the top equation. So I can say, well, not only does the top equation give me the left-hand limit, but it gives me f of 2. So the limit as x approaches 2 from the left is the same as f of 2, so it is left continuous. Now the right-hand limit, I would have to plug 2 into this equation, but that is not the same as f of 2. You would have an open circle at the ordered pair 220, whereas you'd have a closed dot at the ordered pair 224. All right, so left continuous only there. Next page here. There we go. Whenever I'm looking at this one, I can say the limit or let f be the function, again, piecewise function. Linear function 7x plus 5 for values of x less than or equal to 4. It's the rational function 3 over x for x greater than 4. Again, it asks us to compute the left and right-hand limit. For any value of x less than 4, we know we're always going to be plugging it into this function. So I said, well, that's going to give me 7 times 4 plus 5, 28 plus 5, 33. Now the right-hand limit, well, For any value of x greater than 4, you'd have to plug it into this function. Clearly, that's going to be 3/4. Now, again, it's asking if it's left or right continuous, and that's an easy question. You can say, well, since the equal sign is up with the x is less than or equal to 4, it's left continuous only. The values that we have to plug in to get to the right-hand limit are not what f of 4 is. So I can say it's left continuous only. And that's, again, because the limit as x approaches 4 from the left is equal to the function at f of 4. Please don't get confused here and say, well, you plugged a 4 into this bottom one too. I had to find out what the limiting value is as x approaches 4 from the right. But your function doesn't exist down there. It exists up at f of 4. But we plug in these values because f of 4 trillion zeros and a 1, it's going to be ridiculously close to 3/4, so that's still the right-hand limit. For the next one, 15, same type of question, I believe, or actually it's a little different. Gives me a piecewise function again, x squared minus 16 over x minus 4, and then f of x is equal to 3 if x is equal to 4 when that rational function fails to exist. Okay. First thing I did was I thought about this rational function. We know that that numerator is a difference of 2 squares. It would factor to be x plus 4, x minus 4. The x minus 4's cancel with the denominator and say, well, this rational function is equal to the linear function x plus 4 for any value of x that isn't 4 anyway. So I can say, all right, that makes it easier to think about. Now, I can say that we know that there is going to be a discontinuity at 4 unless this fills in the hole in the graph that would exist there. Does it fill the hole in the graph? I can say no. How do I know it doesn't? Because if I try to plug in a 4 into what this function simplified down to, the y value needs to be 8. Well, this is not a y value of 8 down here. So I'm saying it's discontinuous at x equals 4 because the limit as x approaches 4, I meant to plug in a 4 there. It should be 4 plus 4. That should be 8. I will fix that real quick. 4 plus 4 and 8. Either way, even if it was a 7, technically it wasn't an error because it's not equal to 3. So you'd say the limit as x approaches 4 would be 8, which is not 3. Therefore, there's a removable discontinuity at x equals 4. There's a hole in your graph there. And whenever we look at this down here, we say, yes, it is discontinuous at 4, and it is removable. Now, the only way that you would have a problem in which there is no discontinuity is if you could plug the value of 4 into the simplified version of this rational function, and it be the same as your y value given in the second part of the piecewise function. The second part of the piecewise function would be filling in the hole in the graph, which causes it to be continuous. Now, that's the idea of this next question. It's giving you an arbitrary piecewise function in terms of x and c, and it's saying it's the quadratic x squared minus c for any value of x less than 3, and it's the linear function 6x plus 5c for any value of x greater than or equal to c. So now what we are supposed to do is find the value of c that makes this continuous. No problem. How is the piecewise function going to be continuous? What you should be thinking is, well, a quadratic function is always continuous. A linear function is always continuous. But a piecewise function could be discontinuous at the piece where they join up. We need to make sure the left-hand limit and that right-hand limit start and stop at the exact same point. That's what I do right here. I say, well, and this is going to be easy. It's going to be continuous everywhere if the limit as x approaches 3 from the left is equal to the limit as x approaches 3 from the right. What do? I plug 3 into my top function for the left-hand limit, n for x, so it becomes 3 squared minus c. Then I plug 3 in for x in my bottom function, 6 times 3 plus 5c. So now I can see that my top equation would just be 9 minus c, my bottom equation would be 18 plus 5c. I solve for c, I'll add c to both sides and get 6c on the right, subtract 18 on both sides and get negative 9. So 6c has to equal negative 9. Divide by 6 on both sides, negative 9 over 6 reduces down to negative 3 over 2. Gorgeous problem there. I like that one. So you're finding the value of c at which makes the left-hand limit of the top function equal the right-hand limit of the bottom function as x approaches c. Now, the last few problems get super quick. You can see it didn't take me any time at all to work them. For number 17, this goes back and it's kind of like that horrid section 2.3 where you say, if you can just plug the value in at which the limit is approaching, you should do that. So the limit as x approaches negative 1 of 6x cubed minus 5 is 6 times negative 1 cubed minus 5. Gives me 6 times negative 1, or a negative 6 minus 5, for a negative 11 final answer. Number 18, similar, gave me the limit as x approaches 2 of the rational function x plus 8 over x squared plus 2x. Can I just plug a 2 in? Sure. 2 plus 8 is going to give me a 10 in the numerator. 2 squared plus 2 times 2 is going to give me 4 plus 4 in the denominator. 10 over 8 reduces down to 5/4. You're thinking, these problems are not fun. They're really not. I don't like these. I kind of did like the next one, though, because it at least made me remember the exact value for the cosine of pi over, or negative pi over 4 in this case. You got the limit as x approaches pi of the cosine of x over 4 minus pi over 2. And you say, well, all you'd have to do is plug a pi in for x. You'll have pi over 4 minus pi over 2 is the angle. Pi over 4 minus pi over 2 gives me a negative pi over 4. The cosine of negative pi over 4, I'm just thinking, well, that's the angle at which it splits quadrant 4. And at that angle, your cosine is going to be the square root of 2 over 2. That's what we do. Please remember, no wimpy decimal approximations. You have to know your values of cosine and sine of the common angles on the unit circle. My next one, similarly, I just plug the 5 in. I have the limit as x approaches 5 of the square root of x cubed plus 3x. Becomes the square root of 5 cubed plus 3 times 5. Becomes 125 plus 15. Then I get the square root of 140. And then with that, I just said, well, I know 4 is a factor of 140. 140 divided by 4 is going to give me 35. So then I said, this will break down into the square root of 4 times the square root of 35, which is 2 on the root of 35, for our final exact and simplified answer. After that, another similar one, we're plugging in a negative 1 into this cubic equation that's then raised to the 3 over 2 power. No big deal. When you plug a negative 1 in for x cubed, it stays negative 1. So we end up with 1 plus 16 on the inside. And then you say, well, 1 plus 16 is 17. 17 to the 3 over 2, since that's going to be an irrational number, it's the square root of 17 cubed. I just left it as 17 to the 3 over 2 power, and the chief liked that answer. The last two are still, or actually the last one, is still just having us plug in these values, and you say, well, what if I have an exponential function 4 to the cosine of x? Can I take the limit as x approaches 0? Of course. Plug in the angle of 0. You know the cosine of 0 is 1. So the limiting value here is just 4 to the first power, or 4. And if you're thinking, wow, those last few problems were very anticlimactic, John, I totally agree with that. I'm not a fan of those. But please do let me know if you have any questions with any of the problems in this section. The next section is much better because it's algebraic solution of trigonometric functions, where we actually can show our work a little bit better in that section. I think you'll think like me and say it's a fun section. All right, guys, till then.